and welcome my wonderful AP students to possibly the most important video you've watched so far. This video's got two major parts. We're going to talk briefly about your mini lab activity for the day. We're also going to start the kinematics kind of subunit that will give you a lot of information and a lot of thought. As always, you're going to have your physics notebook open. You're going to be writing, taking notes. You're probably going to want colors for this. You'll see why near the end. And not only going to normally rewind, pause, let things sink in, but you're also going to probably make a list of questions of things that didn't make sense. And you're going to ask me these questions during class so that you can rise to the full potential that I know you have. So the first part is going to be our mini lab. Unfortunately, my earlier videos I was recording at school kind of got deleted, so this is more of a tell instead of show, so I apologize for that. This lab's got two major parts. The first part, aptly named, is a walk in the walk. In this, you're going to be walking to match position and velocity graphs from a sample. In other words, I'm going to give you a graph and say, how much do you walk to make this graph? And then you're going to do it and check it using a motion detector. The second part is a good old-fashioned physics thing, rolling down a ramp. We're going to determine how acceleration relates on angle. We're not going to actually figure out on a ramp what the acceleration is of an object rolling down it, because the graph will tell you that. Instead, I want to know the relationship between angle and acceleration and angle and velocity. And even more importantly, I want to understand and have you understand how changing the scenario affects the outcome. Steeper angle, what will happen to the acceleration? Longer track, what will happen to the acceleration? If you have your motion detector at the bottom versus the top of the ramp, how will it change what the graph looks like? And it's these different permutations that sets us apart from the other physics students in the building. And because of this, you're going to be using something called a lab quest. It's pretty awesome. And a motion detector. When you're walking the walk, you're going to have a big whiteboard, and you're going to be the object walking back and forth. For rolling down the ramp, I don't want you actually rolling down the ramp, so instead we're going to use a cart with a note card taped on it. My whole point is that you're going to be figuring out how to use the motion detector and how it relates to the graphs. And also, even more importantly, how the position of the equipment and the equipment itself affects the graph and what you get. The AP's got a couple of questions that are new this year of giving a scenario and saying which lab equipment is best in this situation. And then furthermore saying, if the motion detector is at the bottom of the ramp, which one of these graphs would be correct versus at the top of the graph? Sorry, at the top of the ramp. So it's getting you to think outside your normal comfort zone of not just what do you expect, but also what do you expect when the position of the detector is at a certain place, which I think is an incredibly inventive question. So I hope you're ready to transition because we're about to go into the kinematics. So this is kind of like a major idea that will be in this topic as well as the next one when we have motion both going forward and up or down at the same time. So the word kinematics is the idea of motion. And there are going to be 5 key ideas here. These 5 ideas you've already seen before. The first one is the idea of the initial velocity or V naught. And as you see here, it's a starting or initial velocity of the time segment in question. Time segments will be capitalized for all of these, and you'll see why it's super important later on in this video. The second of the 5 key ideas is the final velocity of the time segment in question. The third, of course, is the displacement, called delta x. The fourth is the acceleration. And the fifth is the actual time of the time segment itself. So these 5 things are mathematically related through calculus, and also through some algebraic equations you're about to pick up today. Write these down, put them in a big box, because these are the biggies. Now, I can teach you as much as I want, but I want to teach you strategies on how to use them and what they mean. So I have 2 major ones, and here's the first one. You're looking at a situation. You're going to make a chart of the 5 variables that can be happening here. Now, so you can write down, V naught, VF, delta X, A, T. My cat just scratched me, holy cow. And that really hurt. But nonetheless, for each one, you're going to include a positive or negative for each one except for time, because time can't be negative. If you don't know a variable, leave it blank. Actually, it really hurts, that cat scratch. So sometimes you'll have 2 blanks, sometimes you have 3 blank. And then finally, if you're trying to find something, instead of putting a number in or leaving a blank, put a little question mark in there to remind you. And my cat you just heard my cat right then. Nonetheless, there are going to be times you're going to have multiple tables in a single situation, depending if there are multiple parts of the motion. And I'll give you an example later on. So don't just assume that you have one table for an entire problem. Sometimes you might have 2 or 3, depending on if the motion breaks up. And finally, once you know 3 of the 5, the physics is done. You could solve the rest using mathematics. And actually, you're going to see there are a couple questions on the AP where they say, can you solve for these things with these givens? You don't actually have to solve for numbers, remember? It's just, can you figure it out? And if you know 3 of the 5 of a given time period or a given acceleration, you do have everything you need. And here's the second strategy, and holy cow, is it a doozy. You're going to love it. You're going to be drawing out number lines and using them to understand what's being asked. Here's an old school GT problem that sometimes gave people trouble. A car going positive 20 meters per second deaccelerates at a constant negative 5.5 meters per second squared by letting up the gas, blah, blah, blah. There are 2 questions here. Find the time it takes to stop, which is not too tough, and then find the distance traveled between the 2nd and 5th second, which takes actually a bunch of thought. So here's our number line from 0 to 12 seconds. Now, why do I put 12 in there? Just randomly. It could be more or less. I don't really care. Now, overall, we know a couple things. You know, the velocity starting is 0. Whoa. The velocity at the beginning is 20. And the velocity at the end is 0. I don't know how much time it takes, so I just put the arrow outside the timeline. It's just a reminder. And the acceleration is a constant negative 0.5. So at every moment here, the acceleration is the same. Now for part A, find the time. I can do it. I know 3 things. The initial velocity is 20, the final velocity is 0, and the acceleration is negative 0.5. If I know 3 things, I can get the rest. But part B is a doozy. Part B is asking me to find how far it is from this arrow to this arrow. And if you notice, I don't really know that much about it. 20 meters per second is not the initial velocity for this time period. So the 2 things I know the time period is 3 seconds. From 2 to 5. And I know the acceleration is negative 0.5. If I know one more thing, I can figure out the displacement between these 2. But I don't know any of the velocities that matter here. So I'm going to use a little bit of trickery and my number line. You can see here, the 20 meters per second is not the starting velocity. I can't use that with a time of 3 seconds, because using this with 3 seconds is from this yellow arrow to this point right here, which is nothing to help me. So there are 2 ways to be clever. Way number 1, I'm going to use the 20 meters per second. I have to because it's something I know. And I'm going to go from the yellow to 5 seconds. That distance represented by the red line up here. I could find that distance or displacement because I know the initial velocity, I know the acceleration, and the time is 5 seconds. Once I have that, I'm then going to find the distance from 2 to 5, which is the blue part, by actually finding the green part, the distance from 0 to 2, and subtracting the green from the red, giving me the remaining displacement. So for the green section of the number line, which is from 0 to 2, time is 2 seconds, the initial velocity is this yellow arrow, and the final velocity I'm not going to solve for, but I am going to solve for the distance. Time, acceleration, initial velocity, that's 3 of the 5 things. And then once I find that distance, and I know the distance from 0 to 5 seconds, I subtract them and I get that distance remaining. The second way is I use the 20 meters per second as my starting velocity. The acceleration I know, it's constant, negative 0.5. And I use a time of 2 seconds, and I find the final velocity from yellow to this blue. Easy, don't even need math for it. You lose negative 0.5 every second. After 2 seconds, you lost 1, 19 remaining. So now at this point, I know the initial velocity is 19 for 2 seconds. I know the final velocity. Well, no, I don't, so I don't care about that. I know the time is 3 seconds. I know the acceleration is negative 0.5, and I could find the displacement. So here are the relationships you're going to be using to actually solve for these. Please write them down, make a big box around them. They're also going to be in the formula sheet you'll be getting very soon. So the first one gives you the final velocity. If you know the starting, the acceleration, and the time. The second gives you your final position. If you know the starting position, the initial velocity, the time, and the acceleration. Remember, if you move this x naught over, you get x minus x naught, and that gives you the displacement. So this one really can say, this one relates to the displacement, these 2 things, the initial velocity, the time, and the acceleration. The final one is the final velocity, the initial velocity, the acceleration, and again the change in position, which is called displacement. You're going to be doing a lot with these, but not always solving for a result. Sometimes you're going to be just figuring out what they mean and how changing one variable affects the others. Remember, this is less mathy solve for a number and more of what's actually happening. So now I'll write down these key phrases. The first one, drop, rest, stop. That means the velocity is 0 for that moment. The phrase constants used a lot. A constant velocity, for example, unless direction is actually changing, the acceleration is 0. So the actual magnitude of the velocity is unchanging. And finally, terminal velocity, if something's dropping in the air, means that at terminal velocity the acceleration is 0. And finally, one last key phrase is look for directional phrases. Up, down, backwards, forwards, speeding, slowing. So now let's take a look at a problem together. Please pause the video, read this to yourself if you don't mind. Alright, look on the side over here. I made a colored number line without numbers to show off what's happening here. The brown section represents when it's in the air, the blue in the water. So this first brown arrow is when it's dropped, this next brown arrow is when it's hit. This blue arrow down here represents the final of the 5 seconds in the water, and this yellow, it should be right next to the blue, but I'm keeping it aside so you can see it, is the start of the last 3 seconds of its descent. So in the air, brown, let's see what we know here. First of all, we know the acceleration is probably gravity. It doesn't say ignore air resistance, but I think it's okay to assume here. And second, we know that the initial velocity is dropped, and that's it. We don't know the final velocity. It isn't 0 when it hits the water because it keeps on going. We don't know the time. We don't know the displacement or how far it went. So that's it. So the brown area is completely unknown. We only have 2 things of the 5 that we need. Now in the water there are 2 different time periods. So if you made a table here, you'd have 2 separate ones for the water. So for the first 5 seconds in the water, which is brown to blue, we know the acceleration is not gravity. It's actually decreasing to 0, not the speed, the acceleration. So you have a changing acceleration here, so we can't even use those equations I gave you because those ones assume constant acceleration. We don't know the starting velocity for the 5 seconds because the start of the 5 seconds is when it hits the water. We don't know that velocity. We do know the final velocity, however. The final velocity is going to be probably that 4 meters per second because that's the terminal velocity after it stops accelerating. So we know the time is 5 seconds for this section, and we know the final velocity. We don't know the displacement, nor do we know the initial velocity, nor do we have an acceleration. It's not 0, it's constantly decreasing till it reaches 0. Now for the final 3 seconds, the yellow to the end, we know the acceleration is 0 because it's at a terminal velocity. Also the phrase constant speed give you a big hint right there. So we know that. We know the velocity is 4, so we know the initial velocity and final velocity are both 4. And finally, we also know the time is 3 seconds. So we actually have 4 things there, which is more than enough to actually solve for anything else we need. And the only one unknown thing is a displacement. So let's go through the letters here. Letter A. Can we figure out the speed of the rock as it enters the lake? Nope. There are 2 sections it applies to, the brown and the first 5 seconds of the blue. Neither one has got the 3 things we need, so that's automatically wrong. Can we figure out the distance the rock travels in the first 5 seconds of its water? We already said, nope. We only know the time and the final velocity. We don't know the acceleration. In fact, it's constantly changing, so you couldn't solve it anyway. And we also don't know the initial velocity of that time. Can we figure out the acceleration of the rock 2 seconds before it hits the lake bottom? Well, yeah. First of all, we know it's 0 because it's constant. But secondly, even if somehow we didn't, we would have enough information to solve for it. Because even if we know an acceleration, we'd have VI, VF, and time. And letter D, the change in potential energy of the rock, earth, water system. What the? But look at the actual wording of the question. Select 2 answers. This is one of these AP questions that's not only choose 2 answers, but also don't actually solve for it mathematically. Since we know A and B are wrong, C and D are right. And look at that. We don't even know about potential energy yet, and we got this sucker. So the answers are C and D. And with that, my wonderful students, you certainly have questions for me. I'll be helping you out with them. You're to get some homework that is similar to these kind of things, and I can't wait to see you, do some lab stuff, and learn some more. Have a great day.